In this video, I'm going to show you how to set up and run a basic crystal growth simulation of zeolite A, such as the one that we can see here. I will show you how to adjust the free energies of crystallization and the supersaturation profile, and to color the crystal correctly. First, open up Crystal Grower and you will get this first tab which shows structure options. And at the top here we've got some information about the structure which we're going to input. First we need to decide whether we want to do a tile or a net simulation. As we're doing a zeolite, this is best performed as a tile simulation. Then you want to browse to find the structure file, which you should already input from Topos. Open that up and read in the structure file, and you should be given this notification down here that the structure file has been read successfully. So now we've input the structure file, we've got a few options which we can put in. The first one is whether we want to insert a screw dislocation or not. In this particular case, as we're just doing a basic calculation, I'm not going to put in a screw dislocation. Then we've got different types of calculations, and I'm just going to do, in this case, a normal type of calculation. Finally, we need to decide what to do about checkpointing of the simulation. A checkpoint file means that after you've run a simulation, if you checkpoint it, you can then subsequently read in that checkpoint file and you can continue your calculation from that point. As we haven't done any calculation yet, we will not be able to load in any checkpoint file, but it would be useful to be able to save the checkpoint file at the end of the simulation so that we can run it again if we want. So we'll answer yes to the second question, but no to the first question. Okay, now we're going to look at some options for the simulation in the next tab here. First, we're going to specify where we're going to save our output files. So we need to browse here to find a suitable folder into which we can put our output. So I will save it in a folder which I've set up previously called LTA for zeolite A, and that means that all of my data output will go into this folder, and then I can give a name, any name I want, to those files. I'll just call these LTA1. You have an option as to how you save all the output files. So there's going to be a lot of output files. The XYZ file, which contains the information about the crystal structure, it's sometimes useful to have this separated out from all the other files. So I like to use the files we saved together in a separate folder, but there are other ways that you can do this. Then we need to start to specify some of the parameters within the program. So the first thing you can do is set up the temperature. So zeolite A is maybe growing at 100 degrees Celsius. Then we need to specify how large the simulation is going to be, and this is done in the number of iterations, and those can either be growth or dissolution steps. And we'll start off here by just putting in 1 million steps to a rather small calculation. You'll also notice here that you have the ability to vary some of the parameters. So if you want to do multiple simulations, for example, you could do a number of simulations where you start at a given temperature, end at a given temperature, and step the temperature up in different sizes, and then this will do multiple calculations. But for now I'm just going to do one simple calculation on zeolite A for 1 million iterations. The next thing is about how the memory is calculated as the crystal grows, and this is quite important. So the crystal will grow in silico, and you need to assign a certain memory size for that in which that crystal can grow. Now, within the program there is an automatic memory calculation. It grows a very small crystal first and then tries to assess how much memory will be required for the complete simulation. And on the whole, this tends to work. It doesn't work in every single situation. Sometimes you need to put this in manually, but for now we will ask it to do an automatic memory calculation. So we'll type yes here, and there's a maximum memory which we will allow it to actually assign, so it doesn't assign too much memory within the computer, and the default number here is reasonably good for most computers. Then we can say whether we want to just have a single frame for the output. That will be the frame at the end of the simulation after 1 million calculations, or whether we want to make a movie. So for now we're just going to record a single frame, and we'll show you making a movie later on. Okay, now we'll look at the supersaturation profile tab, and this allows you to say what is happening in the solution phase during the simulation. And there are a number of set modes for supersaturation here which you can choose. So for example, if you choose mode 1, the supersaturation will start high and then will immediately at the beginning of the simulation come down until it attains equilibrium. You go to mode 2, that would just be a constant supersaturation profile. Or mode 3, which has a constant supersaturation up to a certain point and then drops down towards equilibrium. And then there's just some more complicated modes with different numbers of constant supersaturation steps, attaining equilibrium and then changing supersaturation profile, and so on. And you can choose which one of these you would like to use. So we'll have a look at mode 3 to begin with. We'll also ask the question, do you want an excess supersaturation of any component? Because we're dealing with a zeolite here, which is coming from a gel where there is really no specific components. For instance, if you're looking at calcium carbonate, you could say I've got an excess of calcium or an excess of carbonate. For a gel, for a zeolite, there really is no value to having this excess supersaturation component, so we'll say no in this particular case. Then we just need to set up some parameters for these different periods of the profile. So first of all, we've got this delta mu1, which is the value of the supersaturation in this first phase here. And I'm just going to put this very high. This is in kilocalories per mole. I'll put 100 kilocalories per mole, although this is an exceedingly high value which you'd never achieved. It does allow the crystal to grow very, very quickly in the computer, and I'm actually more interested in the phase then when it comes down towards equilibrium, which is this second phase. So first we need to say the number of iterations at the end of the first period here, so how many iterations from here to here. So let's, for the sake of argument, say that we're going to have 500,000, so that's half of the simulation will be at high supersaturation. Then you need to input the number of iterations to equilibrate, and that's a sort of time constant, if you like, for this decrease, this exponential decrease towards the equilibrium value. And so I'll put that as about 100,000 iterations. So it should achieve in this 100,000 iterations equilibrium, and then we've still got about 400,000 iterations left until we get to the 1 million iterations at the end when the simulation will terminate. So having looked at the solution phase, now we're going to look at the solid phase, the zeolite, and we're going to look in this case at the tile options for the energies. And we're going to have some settings, some basic settings here for the tiles. The first question you ask is whether you want all the QN scaling to be the same. So if you have Q3s or Q2s, do you want all these to be the same? Well, as it turns out for zeolite A, there are only Q3s, so it doesn't really matter. If you were looking at something like ZSM5, where you have Q3s and Q2s, then you'd have to make a decision whether you want those treated the same or not. But we'll answer yes here. Then we ask the question, do we want the scaling for all the tiles to be the same? And this is important for zeolite A because there are 3 tiles. So we could say yes here, and we could give exactly the same energy spacing on the energy ladders for zeolite A all to be the same, in which case we would enter the energy spacing here. So for instance, it could be, say, 2 kilocalories per mole, between the condensation levels on the ladder for zeolite A. But it turns out for zeolite A it's actually better to have different energies for each of the ladders, and so we should first of all put the baseline energy separation back to 1, because this is a scaling factor, and we'll multiply all the other energies up by that scaling factor. And then you should get a list of all the tiles within that zeolite which will have been picked up from the structure file. So in zeolite A there are 3 different tiles. There's the double 4-ring, the sodalite cage, and the alpha cage. And I know some good numbers here would be 8 kilocalories per mole separation for this one, about 5.1 for this one, and 1 kilocalorie per mole for the alpha cage. But you can put these as any values you want, and if you want to actually find out what the best values are, it's a very good in this case to vary these over a certain range, so you can do multiple simulations and then find the best simulation which matches with your experimental data. But for now I'm just going to do one simple simulation with one set of energies. Finally, we would like to colour the crystals, so we check this crystal colouring tab so that the surface of the crystals are coloured as terraces as we would see in atomic force microscopy. So you get asked this first question, do you want to colour the crystal in layers, and we'll say yes to this. But because it's the first time that we've actually run a simulation, we won't be able to colour it. All we can do at the beginning is try to find the relevant crystal surfaces that we want to colour. So we're going to check for the first time this find radio button. Then afterwards, after we've done the first calculation, we should be able to rerun it, because remember we've set checkpointing to yes earlier on, so we should be able to rerun the checkpointed file and hopefully colour it the second time around. Okay, so we should be ready now to run our first simulation. So we just go down here and click Run Crystal Grower, and it should run with all the parameters that we've set up. So it started on the iterations now. It's doing 300,000, 400,000, so it's halfway through the simulation. So the supersaturation will be dropping now towards equilibrium, and then we finish off and do the 1 million iterations. So that's the completed simulation. If you go and look on your desktop now and you find the folder in which we saved everything, which is here, you'll find a time dated folder which has been added to your files. If you open up that, you'll find the files which have been saved from that simulation. There are 2 files and 2 folders. The 2 files at the top, one is a file from which you can reload that simulation at a later date if you want to. The structure file has also been copied into the folder. Then you have a whole list of output files which we can discuss later, and then separately we have the XYZ file which contains the actual simulation that you've done. Now we can look at the output of the simulation we've just done using a veto, and if you want to know how to use a veto, there's a separate tutorial for that. So if we open up a veto and then we load in the file which we've just looked at, so we just navigate around to that folder, that's the time dated folder, the XYZ file, and we open up that XYZ file. We have to set some parameters here, but again, if you look in the veto tutorials, you'll see how to do that, and you'll get the simulation that we've just done. And what we can see here is that the crystal is in colours which are not as you'd see them in an atomic force micrograph. You've got the 3 different cages, the double 4-ring, the sodalite cage and the alpha cage, all given a different color, which is useful to us because we can interrogate where the different cages are on the surface. But it'd be useful also to be able to see these terraces, which are rather difficult to see here, correctly coloured. But in order to do that, we'll have to go back now and do another simulation again and recolour this correctly. What we can see on this particular simulation is that there are three surfaces which have been found. So there's this top surface, which is the 100 surface. Then you've got this surface here, which is the 110 surface, and finally the 111 surface of zeolite A. So these are the ones we're going to have to colour when we go back and use Crystal Grower again. In order to do the recolouring, first we're going to have to edit the colouring file which we have just created. So first of all, browse until you can find the file you've just created. So that's going to be in one of these output files that you've just created. If you look for the one that says facetsfound.txt, and if you read that layer file, you'll get a list of all the different facets that have been found. Now, that first time this is run, the chances are it will have found more facets than you want. For example, if it's found the -100, then it's probably also found the -200, but we only want one of these. The despacing will be half as much for the 200 as it is for the 100. In our case, we actually want the 100, not the 200 file. So in fact, there are quite a number of duplicates here. All these ones with higher HKL are not required, so we should remove all of these ones from the layer colouring, which we can do there. Similarly, down the bottom here, all these higher indexed faces we don't require. And then in the middle here, there's also some extra higher index faces. So there's the O-2O, the O-2, which we don't require, and there's the OO-2, the OO2, and then the O2-2 and the O2O. So all we're leaving is the family of 111 planes. We've actually removed too many there. So we need the family of 111 planes, the family of 110 planes, and the family of 100 planes. You can check that you've got all the families by checking the d-spacing. So a family of planes will have the same d-spacing. So the 111 or -1, -1, -1 here, same d-spacing as the -1, -1, 1. They're part of the same family. And so we just include the three families that we want. And then we're going to save that into a new file, which we can either browse and find one we've already got, or I can just give that a new name so that it doesn't overwrite the previous one. And we save the changes there. Now we're going to colour the crystal, and to do that we need to browse and find that new file which we've just created, and in order to do the recolouring we need to go back to our structure options, and this time we're going to load up the checkpointed file, and we need to browse to find the checkpointed file. So that will be in the same folder, and that will be your checkpoint file which we created. We don't really want to save a new checkpoint file, and if we're going to recolour it we don't need to do a million iterations. So we go to the simulation options and we just set that to 2 iterations, which is the smallest number that you can do. And now we rerun Crystal Grower. It's done the 2 iterations and we'll have created a new set of output files. So having recolored it, when you go back to Avito and we open up the new file which we've just created, so we find the new time dated file, we go to the XYZ file and open that up as before. So we'll see exactly what we saw before, but now we can recolor this, and you go to the video on Avito, you can see how to do this. We're doing it quickly here. We're going to add color coding in. We're going to change color coding to mass type, and we're going to put a range from 0 to 5. And now we can see the terraces which are colored according to their layer type. So here's the 100 surface, which is correct. Down here we've got the 111 surface, which is correct. But if we look here at the 110 surface, it's not quite correct, because we're actually getting two different colors into each layer. So there's a little bit more adjustment that we need to do here. So in order to make that adjustment, we need to go back to our crystal coloring, and it's useful now if we actually pull up the new file that which we've been working on. So that was, if you remember, the file which we saved with the -A at the end. We read that layer file. So this is the one we've just been working on, which was correct apart from the 110 family of planes here. And if we look over to the right, we can actually see two more variables that we can change. There's the number of layers to color. These are all by default set at 4, and that depends on how large your crystal is. You might need more than 4 layers to color a surface. But what we need here to make this final adjustment is this offset to the coloring, and this is a fine adjustment that allows you to choose the plane at which the color actually changes. So this can be adjusted. By default it's set at -0.01, so it's just offset from 0. This can be anywhere between -1 and +1, and I'm going to change that from just below 0 to just above 0 by removing the minus sign. But I need to go through and do that for all of the related planes, of which there will be 12. So there's 1, 2, 3, and there's the fourth one. I'm looking at the D-spacing here to find them. It's the quickest way. 5 and 6. That's the first half of them. And then we've got 7 and 8. 9 here. 10. 11. And finally 12. This is a little bit tricky, but once we've got this correct, we won't ever have to do it again for zeolite A once this is all set up. So we're going to save the changes that we've made there, and then everything is set, and we can rerun Crystal Grower. It's done another 2 iterations on the original checkpoint file. Now we can go back to Avito and load in the new file which we just created. So there should be another output file, and we load that one up and replace the one which we had before, and now you can see that we've corrected the terraces on the 110 facets simply by just moving slightly the point at which the decision to color at a particular plane is made. And so now we have our perfectly colored crystal, and we can now go on and do any calculations in the future on zeolite A using that particular coloring file, and that will always be correct. We won't ever have to do it again for zeolite A. Finally, I'm going to make a movie of the crystal growing at a constant supersaturation. So if you want to do a constant supersaturation, first of all you need to know what driving force to give it. Now we've just run in mode 3, if you remember, which was running at high supersaturation and then down towards equilibrium. So if you go back and have a look at your original set of data files, you'll find inside that set of data files one called del mu, and there you'll see the supersaturation, which started at 100 at the beginning, ran at 100 for half of the simulation, so down to about here, and then it started dropping down towards equilibrium. So if you go down and have a look at the last row of data, you'll see that at equilibrium the driving force was 15.5 kilocalories per mole. So 15.5 would be equivalent to no supersaturation at all, just running at equilibrium. So for example, if I want to run at supersaturation of 4 kilocalories per mole, I'll need to set the driving force as 19.5 kilocalories per mole. So let's do that. We're going to go back to our original calculation. We're going to read in that checkpointed file just as we did before. Then if we go to the simulation options, we're going to run a much larger number of iterations. We'll run, in this case, 10 million iterations. Because we're using a checkpointed file, we'll actually have to assign the size of the box that we're going to require. So I'm just going to make it larger than it was before, and I'll assign it to 401 cubed. That should hopefully be large enough for this simulation. Then we're going to make a movie of the simulation. It's going to ask you the number of frames that you want in the movie, so let's say about 50 frames. Don't make this too large because otherwise it uses up an awful lot of memory when you save it. Where the initial frame, well, let's start the movie at about, say, 9 million iterations, and then it will run on. Do you want to set the last frame equal to the number of iterations? But yes, so it's going to end at the final frame. Then we need the supersaturation profile. In this case, we're going to run in mode 2, which is a constant supersaturation, and if we want to run at 4 kilocalorie per mole supersaturation, we need to make the driving force 19.5 kilocalories per mole. The tile options will just remain the same. They're what we had before. The crystal colouring will all remain the same as we had before. So then we can run the simulation, and that should run for the 10 million iterations. So now we just fast forward through to 9 million iterations, and then we begin to output the frames, and there's going to be 50 of these, which are going to be recorded between 9 million and 10 million iterations. Fast forwarding again to the end of the simulation, we now get to a total of 50 frames output, and the computation is complete. Finally, going back to Avito, we can now load up that new file that we have. So that is here, and we'll see this is a much larger file, 533 megabyte file, because it's got 50 frames in it. And we open that up in Avito, and now we'll be able to see it takes a little bit longer to load up because there are 50 frames to load, and when those are complete we can run the movie and we can see the crystal growing at a supersaturation of 4 kilocalories per mole. The colouring on the surfaces is correct, and we can just use that same colouring file whenever we run zeolite A in the future. We don't have to do that again. And that's how you do a basic calculation for a zeolite.